Lagrangian of a spinning symmetric top. Consider we have a symmetric top as shown, which is fixed around origin O because we are not interested in lateral position. The symmetric top is subject to gravity, mg, positioned to the center of mass, principal axis E3, which has a different moment of inertia, forms angle theta with respect to axis z. We have shown that in the body frame, angular velocity can be written in terms of Euler angles, phi, theta, and psi, as following. Minus phi dot sine theta. For second component, we simply have theta dot. And for the last component, we have psi dot plus phi dot cosine theta. And of course, for the angular momentum, we simply multiply components of omega by the corresponding principal moments of inertia to get minus lambda 1 phi dot sine theta, lambda 1, because lambda 1 and lambda 2 are the same, theta dot, and lambda 3 psi dot plus lambda 3 phi dot cosine theta. Our job is to write the Lagrangian for this system, which we can do right away. We know that potential energy is simply given by mg times r, distance to the center of mass, times cosine of angle theta. For the kinetic energy, we know that we can simply write it as half of L dot omega in the body frame, where our body frame is defined along the principal axis E1, E2, and E3, which simply gives us half of lambda 1 omega 1 squared plus lambda 1 omega 2 squared. Remember, we are dealing with a symmetric top. Lambda 1 is equal to lambda 2 plus lambda 3 omega 3 squared. Therefore, we get for our Lagrangian half of lambda 1 times phi dot squared sine theta squared plus theta dot squared plus half of lambda 3 times psi dot plus phi dot cosine theta, and all of it is squared, and minus potential energy mgr cosine theta. Let's look at some of the symmetries of this Lagrangian. We want to identify cyclic variables. We know that the cyclic variables are both phi and psi, which give us momenta conservation for p phi, defined as partial derivative of Lagrangian with respect to phi dot. We simply get lambda 1 phi dot sine squared theta plus lambda 3 times psi dot plus phi dot cosine theta multiplied by cosine theta. And this should be a constant. Also, momentum p psi, which is defined as partial derivative of Lagrangian with respect to psi dot, gives us lambda 3 psi dot plus phi dot cosine theta. Furthermore, we can identify component p psi as lambda 3 times omega 3. We can see this from the expression above, which is nothing other than angular momentum component number 3, which should be a constant of motion. we can also rewrite p phi in the following form. We can write it as minus lambda 1 omega 1, this here, times sine theta, plus lambda 3 omega 3, this here, times cosine theta, which is nothing other than minus L1 sine theta plus L3 cosine theta. Let's recall a relationship between unit vector z, unit vector E3, angle between them is theta, and unit vector E1, which is perpendicular to E3. Here we can notice that component L1 times sine theta with a minus sign gives us this little projection here, whereas component L3 times cosine theta gives us this projection along z. So by combining these two together, what we get is nothing other than the projection of vector L along z component. Thus we identify these two momenta, which are constant, with the space component Lz, vertical component of the angular momentum, which will be conserved, and with the body component L3 of the angular momentum, which is also conserved.